Hi, this is Faizan Azim and welcome to a series of lectures. So, in the last video we saw, quantum field cosmology. We had two videos. This is officially the third video and second lecture. Okay. So, effectively in the first lecture we saw how we speak about manifolds. Yes, so we saw a few things maybe in quantum field cosmology. So, I began giving you an objective course structure. I told you how it's going to be like, objectively, and then we began with some basics of classical field theory. Yes. So let me just touch upon those things once again. I'll just give you the highlights of what exactly happened about classical field theories, and then we can probably move on. So you know how we define classical fields is by using a concept of abstract algebra. Okay. So in abstract algebra, you got a few elements like groups. This is the elements of abstract algebra. You got things like groups, rings, fields, vector spaces, and modules. We'll be making a playlist on abstract algebra as well, but then assuming that you at least know some basics of this and you understand the definition of fields. Well, I gave a mathematical definition of a field. So what happens in a field is a field we denote with a phi. Okay, so a phi field is a mapping that you get from a manifold, which is of n dimensions in our case, because I think I need to make about a lecture on how exactly it differs within lectures of a theoretical physicist and a mathematical physicist. So when deal with this as a mathematician, we'll try to be as much generalized as possible and we'll try to be as much abstract as possible. So we'll do one thing, we'll have manifolds of n dimensions. Mostly physicists go for space-time, which is 1,3, right? Or you call this Hilbert space, Minkowski space. But yeah, let's have a manifold of n dimensions. So a phi is a mapping from manifold to S. Now S is what we call a target space. Yes? So we also saw how we classify fields based on what our target space belongs to. Yeah? We saw scalar fields where our target space belongs to real numbers. We saw vector fields where your target space belongs to real numbers with vectors, that is at every point on your space it's represented with a vector pointing in a certain direction. So we saw scalar fields, we saw vector fields, we saw what happens when it's in a surface of a sphere. We call this as a sigma model. And then we said we can generalize the things of the scalar fields and vector fields into what we call tensor fields. And we spoke at the the end part of the lecture, we began with some of the examples of vector fields, where we use differential equations in vector fields. We began with Maxwell's equations, which is discussed for a while. So we ended our lectures with where we talk about a few vector operators. Let me just remind you, and then we can move about, right? So vector operators. So what are the basic vector operators that we spoke about? The first one was the gradient. So this is the vector operator. Maybe it's acting on a vector this. So how do you define it? We'll see it maybe in tensor rotations. So you got a gradient. We have divergence. We'll all give an analytic meaning to what exactly these stands for. So divergence is given with a dot. Good. So all this happens with the first vector operator with this inverted triangle, which we call this nabla, or So there is second one, which is a Laplacian. We'll see with both the cases of scalar Laplacian. A is a scalar. This is also known as a del operator. This is a Laplacian. Yeah, the Laplacian operator. And second, we will see this vector. This is called the scalar Laplacian and vector Laplacian. Good. With this, we saw how we modeled classical electrodynamics. Yes, we saw how we modeled classical electrodynamics using Maxwell's equations. We'll get back to all of this. Have some patience. We understand perfect rotations, some sexier rotations, and then we get back to this. Yeah. So Maxwell's equations. Maybe something that's written on my T-shirt. Yeah. The first one is the Gauss law. These are the four Maxwell's equations, which are perfectly, most elegantly described by using these vector operators. Yeah. So I also said the modeling of vector fields happen on this. Interesting cases. We'll also see a very interesting model, on a sigma model. Maybe in this case, what happens is your target space belongs to, we saw what happens when our target space belongs to the surface of a sphere. Yeah. So what happens if it belongs to the surface of a hypersphere? Sn, a hypersphere with n number of dimensions. We know how hard it is, to intuitively imagine what a hypersphere looks like. In this case, we need to also understand the concepts of, sphere packing. We know we have a little bit of idea of sphere packings only in, 2, 3, 8, and in 24 dimensions. Yeah, now this is something that very often we came up with. So we'll also analyze what happens when your target space belongs to the surface of a hypersphere, and when it also belongs to the surface of a hypersphere, which is infinite dimensional. These are extremely interesting things. Maybe it's just like, topology is how you see a sphere to be. And when you take up some part of the sphere, if that is, too small, if this thing is too small, then you can consider, as compared to the surface of the sphere, you can use the Euclidean approximation. You can consider it to be a Euclidean space, and for all the distance measures, you can go up with the Euclidean metric. Yes, Euclidean metric being for any dimensions. Yeah. So that's what happens. But what happens if the surface, this area that we took up, I'll just show this with a normal vector. If this is considerably big as compared to the radius of the sphere, okay, in this case, we need to take up some non-Euclidean geometries. Which I will be lecturing about because I have to, because this is extremely complicated. We need to at least touch upon almost every advanced branch of mathematics. And I'll just tell this here. So non-Euclidean geometries, including the hyperbolic geometry. We see this in differential topology. Okay, differential topology being the actual language of quantum field cosmology. If you want to understand quantum field cosmology, you need to be acquainted with differential topology. Right? So in differential geometry itself, we define the concept of curvature. So if a curvature is 0, you can approximate it to a Euclidean space. But if a curvature is negative, it's hyperbolic. Yeah, you get a surface to be getting a space to be hyperbolic. So you need to understand hyperbolic geometries for this, which Carl Friedrich Gauss came up with in maybe 1770s. Yeah. Then you also need to understand Riemannian geometry. And this is super interesting. You also see this in general theory of relativity. General relativity is basically, your Riemannian geometry. Yeah. And gravity is considered to be a curvature in Riemannian geometry. You got a Riemannian space. Yeah. And the curvature in this is called gravity. So we need to be acquainted with these two things. Yeah. And I need to tell this, in a way, for a mathematician, understanding quantum field cosmology is simply trying to understand, is simply being perfect, as much as possible, extremely rigorous with differential topology. To understand differential topology, we need to be acquainted with a few mathematical objects like tensors, which will begin in this lecture. So if you're talking about differential topology, you need to be acquainted with a couple of mathematical objects. The first one being tensors. For the next 5 to 7 lectures, we'll only be talking about tensors. It will be tensor analysis basically. Well, this is too short of it. I don't think anybody can complete it in 7 lectures, but we'll try as much possible to do it in 5 to 7 lectures with lectures being a little bit longer. So what happens is, we can probably begin a tensor analysis right now, but also with this, let me just tell you, it's extremely important for us to understand DEs, differential equations. Again, I need to lecture on this. Maybe again this will run to 5 to 7 lectures. Again, as usual, every time I mention, I give you a list of lectures. It's always going to be plus or minus 2, with a high probability of it being plus 2. Yeah, it could run to about 9 to 10 lectures. This should run to about 6 to 7 lectures, maybe. Yeah, let's just see how it happens. So with DEs, we need to see both the kinds. We'll see ODEs, that's ordinary differential equations, and PDEs, partial differential equations, and we'll also see ways, attempts to solve nonlinear partial differential equations, nonlinear PDEs. We'll see both in fact, nonlinear ODEs and PDEs. Yeah, we need to understand nonlinear differential equations. That's the essence, basically. So I can do one thing. I can either start with differential equations or I can start with tensor analysis. So let's just see. Maybe we will begin with differential equations. So we'll begin with differential equations. We'll understand differential equations. The next 5 to 7 lectures, we'll understand tensors. Because we need to understand differential equations in that manner. Maybe after that, we can acquaint ourselves enough to understand the basic of topology. So we'll understand algebraic topology in that sense. We'll get about introduction to topology. We'll understand algebraic topology. This is extremely important. You see the basic definition, the built-in definition of a field was a mapping from a manifold. So if you don't know what topology is, it's extremely impossible almost to understand field theories. So we will acquaint ourselves with algebraic topology, then moving on to differential topology. Because we know what DEs are. It's just differential, methods of using topology. So that's the point. Okay, we'll begin with the DEs, that's differential equations. So what are differential equations? Well, it's a system of equations having a differential terms. And the simplest of that being y equals, or you can consider, dy dx equals f of x. This is the most simplest differential equation that you can encounter. How do you solve this? Use the basic integration, right? The first integration. Do dy equals f of x dx. And then you integrate the term with, so you get y equals integral f of x dx. So this is the most basic differential equation that you can get. You can also end up getting differential equations like, so maybe in this case what happens is you are using an indefinite integral. So you add a constant plus c. Yeah. So more on differential equations, I'll give you a few things to do. Maybe you can go through a lecture from Oxford on, I don't know what is it, it's the first year Yeah, so he speaks about differential equations. Basically, he says that yeah, it has intro to calculus. And also watch analysis pretty from the same University of Oxford. Well, they go in detail with differential equations. Good. This is the first order differential equation. What happens when you have a higher order differential equation? Maybe in that case, yeah. Let's see from the physical examples from physical sciences. Newton's laws, right? Newton's second law. What happens in that case? So it's F equals dp dt, right? Well, this is a linear differential equation of order 1. You can also do something like F equals m d2 dt squared of r. Well, it's basically F equals m linear. And in this case, you can write A as dp dt or as a second order differential equation as d2r dt squared. Right? So this can be an example of second order differential equation. You can also have these sort of examples in cases of electric circuits, in fluid mechanics. You know, so basically every time you take up a class on calculus, okay, in your university calculus, the end product of your entire course in calculus is to acquaint yourself with understanding differential equations. The whole purpose of calculus is for you to understand differential equations. That's the crux of calculus. Yeah, that's the essence of calculus. You understand differential equations. You understand. You understand differential calculus. You understand integral calculus. Is all molded down for you to understand and appreciate the beauty of differential equations. Yes, Newton's law of gravity, F equals gmm over r squared dr. Yeah, this is where, while he was trying to understand this, he understood the concepts of limits and differentiability. And I think ever since then, almost every equation in physics, it's just every equation in physics without any exception, is a form for differential equation. So, yeah, we can talk more about differential equations. So, we can understand more about differential equations in a playlist that I'll be making. I'll be very soon making a playlist on calculus. I'll be calling it advanced calculus. Yeah, I'll be taking up a playlist called advanced calculus very soon. Maybe within a few weeks or something. So in this playlist, we'll explore more about these differential equations and multivariate calculus. Yeah. So we'll just take up a question maybe, so that we enjoy differential equations. Maybe try integrating this. You can try integrating this, right? What do you do? What are the common techniques you use in integration? By-part integration, or you use a functional rule, right? In this case, it's by-part integration. So, by-part integration is something like this: integral first, second dx. Get it? So it's integral first into second dx gives you integral of first dx minus integral of differential of first times integral of second dx. How do you get this? You get this from the product rule, the Leibniz rule from differentiation. So how do you integrate this? So it's first, this. First integral of second dx. So the first here is x squared. The integral of sine of x is negative cos of x minus integral of derivative of first. Derivative of this will give you 2x. And integral of second dx. So integral of sine of x is cos of x, and it's below. Minus all over back again to this. So I'll end up writing with the integral of sine of x is cos of x. Right? So use the product rule again. First, the integral of cos of x, so the integral of cos of x, sine of x, minus the integral of derivative of first. We could do something, right? We could take out 2 common outside. We could take us 2 out. x cos of x dx. So first into integral of second. So first is x and the integral of x will be 1. Right? First into integral of second minus integral of now the derivative of first. The derivative of first is 1 into integral of second dx. What is the integral of cos of x? Sin of x dx. And this integral of sin of x is negative cos of x. See, at the end, the final result you got was negative x squared cos of x plus 2x sin x minus, so integral of sin of x is minus cos of x, so you get a minus there, so you get plus cos of x. Why did I take this example up? I was just watching a playlist of Oxford, so the guy solves this, maybe that's why I just took this up. So it's nice you acquaint yourself with techniques of integration and differentiation. Well, yeah, let's just hope the playlist comes up. And yeah, you might have got how exactly we move about with differential equations. And we represent non-linear differential equations with a gradient. Okay. At this point, I guess I need to tell this to you. So the gradient of any vector A vector. You see this in multivariate calculus actually. Maybe let me just tell this. Yeah, alright. Maybe at this point the notations that you're seeing are the notations that are used in tensor analysis. So you can imagine the fact that you can start believing that you are entered into tensor analysis. So let's just call this thing analysis. Let's just call it tensor analysis. The first factor, why you call it analysis, not tensor calculus. There's a difference between analysis and calculus. On a very rough scale, analysis is calculus taken to a next level, an upgraded version of calculus. You take up with a lot of rigor. There's a lot of rigor in analysis. Analysis is basically calculus plus rigor. You see rigor in terms of abstraction, you see rigor in terms of generalization, you see rigor in terms of proofs, theorems, you get all those stuffs. So that's why analysis. Analysis, in the playlist of advanced calculus, we'll also see analysis. Maybe have another playlist on analysis. We'll do it on numerical analysis, including real and complex analysis. We'll discuss functional analysis. And we'll, after functional analysis, I was just planning to go through tensor analysis. We'll see if we can cover almost everything in this series. It's fine, it's completely fine. But if you're not able to do that, maybe I can make a series of lectures only on tensor analysis. At this point of time, we need to realize the course that you're working on is Field Cosmology. And all these things simply build up as a part of this. It has to be there, right? I can either say, yeah, I hope you understand tensor analysis perfectly fine. If you want to read this, give you a study material. Hope you, of course, if you are taking a course upon Field Cosmology, you need to know differential equations. Yes. You need to understand differential topology. Great. Differential calculus. Great. I can probably just begin from differential topology and then move on understanding manifolds and fields. But that's not what I'm trying to do. I'm trying to give you an insight through every concept that we're going to use. We'll see how far will we go in this approach. So in tensor analysis, what's a tensor? The formal definition of a tensor is a tensor is an array of functions. Okay. An array of functions. Great. Why do you use them? One, because of the notations. They're just amazing. Once you understand vector analysis, you find there are a few notations which turn out to be a bit boring and not that trendy, not that enjoyable. The first and the most important thing that a mathematician enjoys in tensor analysis is the number of notations and the way you use them. Yeah, you see, Einstein's theory of general relativity is acquainted in 10 equations, 10 differential equations that Einstein wrote. They're called Einstein's field equations. But using tensor analysis, it boils down to something as simple as g mu equals 8 pi g over c to the power 4 t mu, where g mu is called Einstein's tensor and t mu is called a stress energy tensor. You might have seen this is a really popular one. So you see 10 differential equations, 10 field equations just came down to one simple elegant equation. That's the power of tensor analysis. Well, the motivation of subject This is enormous, right? In fields like differential topology, you cannot do anything without tensors. You need tensors in differential geometry, you need tensors in differential topology. If you want to define what a curvature is rigorously, you need to use the concept of tensors. Also, while extending your fields from scalar fields to vector fields to generalizing them to something called a tensor field. Okay, so you got a tensor field equation, right? So, well, that's just amazing. I don't know what to say. The motivation is extreme for tensor analysis. So, we might begin with a couple of notations for tensor analysis. We'll append ourselves with a couple of notations. Yeah. We'll begin with a tensor notation. How do you represent it? So the first is I need to give you a clear insight of what a vector is. Okay. Don't imagine vector to be a list of numbers or something. Vector is basically imagine it to be an object, maybe something like this chalk. Okay. A mathematical object, which is God knows what. Okay. And you use it to represent a couple of physical quantities. Maybe like your position. You call that a position vector. And they're just mathematical objects, and you can consider them to be geometric objects rather than considering them to be some sort of arithmetic axiom. Okay, don't consider them to be some sort of arithmetic axioms, not a string of numbers or something. Consider them to be a geometric object, which just change the way you look at geometry. So you can talk about a vector this way. Okay, let me just tell you two things in tensors. You need to understand these two things in tensors. One is called the order of a tensor. Order or rank. Yes, order or rank of tensor. So a tensor of rank 0 is called a scalar. Right? A tensor of rank 1, rank or order 1, is a vector. And a tensor of anything greater than rank 1, anything greater than this, is represented with a matrix. Well, these are all elements of linear algebra. You should have seen them in linear algebra, right? Maybe transformations of vectors, transformations in matrices, all of them you've seen in linear algebra, but this is not a course on linear algebra. You take them, you upgrade them to, extreme levels. Yeah, you don't see matrices as the way you saw them in linear algebra. So that's why I never lectured on linear algebra. I took them directly to tensor analysis. I don't know, it's supremely, debatable on the fact should I have done that. I don't know. But yeah, in this way you see them in an extremely different picture. And then this is the first one about tensors. The second thing about tensors is dimensions. You can have dimensions